Alright, this is a tutorial for an external flow over an airfoil, compressible flow over an airfoil. Actually, the geometry is just an airfoil and the mesh is already created. What we have done is just to load up the mesh in the Ansys Fluent. And if you look at the mesh itself, if you go to this, for example, scale, you see that the scale of the mesh, the extent of the domain is from -20 to +25 in X and -30 to 30 in Y. And if you look at the problem description, for example, and here is my problem description, you see this is the airfoil of the chord of like 1 meter. The angle of attack is something like 4 degrees and the Mach number is 0.8, which implies that the that the flow is transonic. So if I go back to my Fluent, so, and you see that the mesh is quadrilateral. What I would like to start with is the fluid, or yeah, can start with the fluid, and this is actually air, typical air, but instead of constant density I would go for ideal gas for the density, and instead of constant viscosity I would suggest to use this model, Sutherland, and I'll keep the reference viscosity, reference temperature, and effective temperature for this model, Sutherland law, as default. So I press OK, and the rest I will keep constant and like default value. So I'll just change and create. Let's make sure that this is changed. Yeah, this is changed. Okay, so then next would be the model, or let's start with general. The type of the solver I would like to choose for this simulation is pressure based. Actually, pressure based in connection with this coupled option for the pressure velocity coupling is a good alternative to density based for high speed aerodynamic problems. And in this simulation I would choose for pressure based plus this coupled options for pressure velocity coupling. And next would be to choose the model. So if I go to viscous, I would go for Spalart-Allmaras one equation. Actually, this Spalart-Allmaras equation is basically or specifically designed for aerospace application that involves wall-bounded flows, and according to the experiences it has shown very good results for boundary layers that are subjected to adverse pressure gradient. So in this tutorial we would like to choose this model, and for this production term I would go for strain velocity based, strain vorticity based, and I press OK. So you can notice that the energy is set to on, because when you change the air, when you change the properties of the air from constant to ideal gas, this energy were set to on automatically, because the energy is now important because you have chosen ideal gas and all the properties are dependent on the temperature. So you can see that energy is already set to on. And then what we would like to continue with is actually the boundary condition. If I go to the pressure far field, so the Mach number was 0.8 if you remember. The gauge pressure I would keep it as 0 because this is a gauge pressure at atmospheric pressure. And then for the x component of the flow direction, this is the cosine of 4 degrees, actually the angle of attack, and that is 0.976. And for the y component, which is the sine of the angle of attack, it is 0.9 0.06 and 9976. And for the turbulence, I'll keep turbulent viscosity ratio to 10, and that should be between 1 to 10 for external flows, external compressible flows, and I press OK. So the wall bottom and the wall top, which are the wall of the airfoil, are set to wall boundary condition, and I'll keep it as it is. I think I forgot one thing, and that is the thermal, and the temperature is 300 Kelvin, and I'll keep it. And the reference value, this reference value is useful when you want to calculate the drag and lift. Actually, these are the values that is being used when you normalize the coefficients. So I'll compute it from the pressure far field, and these are the reference values. Make sure to change the temperature to 300, and yeah, I'll keep the rest as it is. Reference zone fluid 16, and then I'll go to methods. So as I said, when I choose this pressure-based solver, I said that this is good in connection with this coupled solver for pressure velocity coupling. And then what I would like to change here as well is this modified turbulent viscosity. I'll change it to second order upwind, and then I'll pick this pseudo transient as well, which is a good thing in order to have a better convergence in the solution. And then what I would like to do is to go to control and change this actually this density from 1 to 0.5, the relaxation factor, and modify turbulent viscosity to 0.9 if I'm not wrong. Yeah, I'll change this to 0.9. Actually, this is I'm increasing the turbulent viscosity, this modified turbulent viscosity, and this means that you will get a better, quicker convergence, but perhaps not as accurate or not as good convergence as you had with the lower under relaxation factor. But for this tutorial, this is tested, and I would like to have it like 0.9. Yeah, I think we are good to just initialize the solution. I'll pick with the hybrid initialization. And then in this tutorial, I would like to use this FMG initialization as well, and that is located under, if you press enter on your command prompt in your console and then type solve, and then you will see you have several options here. Then you need to type initialize. Then if you press enter again, you see that this FMG initialization. Why do we use this FMG initialization, and what is it actually? This is something that you need to go through the help in Ansys Fluent to understand how this FMG algorithm works. But the reason that we are using it now is because it helps to have the better, or to have something as an initial solution that will help to reach the final solution or the steady or converged solution at the end much faster. So I'll set this FMG initialization. The number of multi-grid levels, I'll keep it as 5. Residual reduction on level 1 is 0.1. I think I'm fine with that. The number of cycles on level 1, instead of 10, I'll go for 100. The same for reduction on level 2, instead of 50, I'll go for 100. Level 3, 100 is fine. level 4 500 is fine, level 5 500 is fine, and FMG current number, CFL number 0.75, and that is fine. And I need to enable FMG variables. I'll set this to yes. So all the definitions and how this FMG works, actually you need to go to the help. This is quite not very difficult, but this is something that you need to study yourself and read it yourself to understand. Press yes. So the solution is now initialized. So if I go to run calculation, let's run it for like 50 iterations for now, and then I would go back to this report definitions and create report definitions and report plots. The reason that I ran the case for some 50 iterations before monitoring the CD, like the drag coefficients and lift coefficients and all other surface reports, is that because in the beginning of the iterations the solution is not that converged. So I'll run it for some few hundred or few tens of iterations to get rid of all these not very converged solution in the beginning. And then later, when you plot all these surface reports, drag coefficients, and etc., you would see it's actually easier to track the convergence of the solution. So now I'll go to report definition. Let's go to residual first, and then I'll change all these absolute criteria to something a little bit lower in order to have it not converge before the final iteration is done. And then I'll go to report plots, or just monitor. I'll go to report definition, right click, and then new, and then I'll go for force report and then drag. So I'll call it CD1, and the wall zones, I'll pick both of them, and report output type would be drag coefficient, and I make sure that I check both report file and report plot. And the force vector, I have to change it again to make sure that this report is actually parallel with the external flow, and that is 0.9976 for X and 0.06976. I press OK. I'll do the same thing for the lift. I pick both of them and I call this CL1, and this time actually would be minus 0.698, and then for the Y would be the same 0.9976, and I make sure to report files and report plots. If I go to post processing, let's make a post plot, a contour plot of pressure, for example, and I picked this field. I think I need to choose this one as well. Yeah. So if you look at this contour plot, you see that already after 50 iterations, on top of the blade, there is a very low area of there is area of a very low pressure, and that is mimicking the shock in the airfoil, on top of the airfoil, and this is something that was expected at transonic solution. At transonic flow, you would see a shock probably on top of the airfoil. This is something known from before, but Uh, what I would like to do is to run this simulation for some 300 more iterations and just observe the report definitions of CL and CD and see how the problem is converging. But this since this CD and CL are average values and are integral values, probably it will not show the convergence as good as, for example, if you plot something like velocity in the vicinity of the wall after the after the shock, just downstream of the shock. So what I would like to do is, in addition to plotting the CD and CL, I would like to create a vortex, a point just after the shock, downstream of the shock, on top of the wall, and plot the velocity of that point to see how the velocity downstream of the shock is fluctuating, and in order to see if the problem is really converged or not. So in order to do that, in the post-processing, I'll go to create, and then I'll click on point, and actually, since I know the exact position of this point that I would like to create, I'll just go to X and Y, and I put point 53 for X and point 051, and I'll call it downstream shock. For you that you don't know this exact position from before, what you need to do is to select the point with mouse and just click on select the point and go around and zoom on this area and click on the points and see where exactly you want to locate your point and report your velocity at that area. But since we know this exact position, I'll just put this X and Y, and I click create. If you want to look at that now, I'll go to display, and what I do is to select this wall bottom and top and this point that I created, and you see that this point is, let me zoom, see where it is located exactly. So you see, if I plot the mesh as well, let me plot the mesh as well. So you see, this is located on top of the wall, on top of the top plate, and right after, right below the first cell or the first mesh in the in the flow field. So I'll go back to report definition. I right click and I click new. This is a surface report of a vertex average, and I'll pick the surface or the point DS shock, and what I would like to plot is the velocity, then the velocity magnitude, and I make sure to report the file and report the plot, and I press OK. So I think I'm fine. I'll just change the name to point. I think I'm fine to run the simulation for some 300 iterations, and we can take a look at the results straight after the simulation is done. So I'll press on calculate. I'll continue the solution, and you see the residual is decreasing. Here is the drag coefficient. Here is the lift, and here is actually the velocity of that vertex average. Okay, solution is completed. So we reached the residual of 1 e minus e7, that or minus 6 that we have already set in the residual here. If you want, we can make it a little bit smaller, and then run the simulation for some 100 more to make sure that the solution is fully converged. So the drag is now constant, is showing a fully converged solution for the drag. It's the same for the lift, and you see for the velocity as well, it's not oscillating that much and it's almost constant. So I think the solution is we can accept it as converged, and we can take a look at some like contour plots of the pressure, for example. What you need to do is to zoom in this area and see the converged solution of this shock phenomenon on top of the blade. You can also take a look at, for example, XY plot of y plus. You need to go to turbulence, and then you plot the y plus of wall bottom and wall top, and you save plot. What you need to do is to go to curves, because here you can see you see only the lines, which are not that nice. Instead of the line style, you go for symbol. This is for curve 1. For curve 2, the same thing. Have two curves. Then apply, close, save and plot. And what you see here is that actually for the white one is for wall bottom and the red one is for wall top. You see that the y plus in most of the area is above 30, especially for the wall bottom, and this is actually desired. We don't want something between y plus 1 and 30, because of this special model, or the special viscous model that we have used here. Either the wall y plus should be less than 1 or above 30. And since here most of the wall y plus is above 30, we can accept this solution and be happy with the wall treatment in this solution. You can plot different stuff, vector plots, contour plots, and every other things that you know in the post-processing. But this tutorial is ended here. I hope you have learned something here. You have learned how to use this FMG initialization method, how to set up an external flow on top of an airfoil for the Mach number of transonic flow, 0.8 between 0.8 and 1, and how to report the definitions and monitor the residuals and the report plots. Until next.